Properties of chords and arcs. Activity 1. Draw any three chords of different lengths of a circle with center O. Draw angles AOB, POQ and ROS. Measure the lengths of these three chords and also the measures of the three angles so formed. Having written these measurements, what do you observe? You may now intend to infer that equal chords subtend equal angles at the center of the circle. Proof. Let AB and CD be two equal chords of a circle with center O, and angle AOB and angle COD be the two angles subtended by these chords at the center of the circle. We shall prove that angle AOB is equal to angle COD. Consider triangles AOB and COD. These two triangles are congruent using SSS congruence criterion. The converse of this theorem is also true. Theorem 2. Converse of Theorem 1. If the angles subtended by two chords at the center of a circle are equal, then the two chords are also equal, that is, of the same length. Proof. Let AB and CD be two chords of a circle with center O, and angle AOB and angle COD be the two angles subtended by these chords at the center of the circle. We shall prove that chord AB is equal to chord CD. Consider triangles AOB and COD. These two triangles are congruent using SAS congruence criterion. This gives chord AB is equal to chord CD. Activity 2. Draw a circle on a tracing paper. Let O be its center. Draw a chord AB. Fold the paper along a line through O so that a portion of the chord falls on the other. Let the crease cut chord AB at M. Measure the two angles OMA and OMB and also two portions AM and BM. Having written these measurements, what do you observe? This concludes that the perpendicular from the center of a circle to a chord bisects the chord. Proof. Let AB be a chord of the circle with center O. OM be the perpendicular drawn on the chord AB. We shall prove that chord AM is equal to chord BM. Join OA and OB. Consider triangles AOM and BOM. These two triangles are congruent using RHS congruence criterion. This gives chord AM is equal to chord BM. This theorem enables us to locate the center of the circle. The diagram below shows a tracing of a broken circular plate. We locate the center and hence determine the radius of the circular plate by marking 3 points A, B and C on it. And drawing the perpendicular bisectors of AB and BC. The intersecting point of the two perpendicular bisectors is the center of the circular plate. This also enables us to construct a circle passing through 3 non-collinear points. The converse of this theorem 3 is also true. Theorem 4. Converse of theorem 3. The line drawn through the center of a circle to bisect a chord is perpendicular to the chord. Proof. We are given that AM is equal to BM. We shall prove that angle OMA is equal to angle OMB, that is equal to 90 degrees. Consider triangles AOM and BOM. These two triangles are congruent using SSS congruence criterion. This gives angle OMA is equal to angle OMB. Since these two angles are supplementary, each is a right angle. Thus the result is proved. Activity 3. Draw a circle of any radius on a tracing paper. Draw two equal chords AB and XY of it. Draw perpendiculars OM on AB and ON on XY. Measure the two line segments OM and ON. Are these two line segments equal? The two lengths are equal. Thus, equal chords of a circle are equidistant from its center. We can prove this result logically. Theorem 5. Equal chords of a circle are equidistant from its center. Proof. Let AB and XY be any two equal chords of a circle with center O. Let OM be perpendicular to AB and ON be perpendicular to XY. We need to prove that OM is equal to ON. Since OM is perpendicular to AB, by Theorem 3, OM bisects AB. So, AM is equal to BM is equal to 1 by 2 AB. Similarly, ON is perpendicular to XY by Theorem 3, ON bisects XY. So, XN is equal to YN is equal to 1 by 2 XY. Further, AB is equal to XY gives BM is equal to YN. Join OB and OY. Consider triangles OMB and ONY. These two triangles are congruent using RHS congruence criterion. This gives chord OM is equal to chord ON. Corresponding parts of two triangles are equal. The converse of this Theorem 5 is also true. Theorem 6. Converse of Theorem 5. Chords equidistant from the center of a circle are equal in length. Proof. In the figure, we have first drawn two line segments OL and OM of equal length and lying inside the circle. Thereafter, we have drawn chords AB and PQ of the circle perpendicular to OL and OM respectively. We need to prove that chord AB is equal to chord PQ. Since OL is perpendicular to AB by Theorem 3, OL bisects AB. So, AL is equal to BL. Similarly, OM is perpendicular to PQ by Theorem 3, OM bisects PQ. So, PM is equal to QM. Join OB and OQ. Consider triangles OMQ and OLB. These two triangles are congruent using RHS congruence criterion. This gives chord MQ is equal to chord LB. Corresponding parts of two triangles are equal. Thus, two chords are equal in length. Let us now take up some examples to illustrate the use of these six. Question 1. In the figure, M is the midpoint of the chord AB and PQ is the perpendicular bisector of AB. AB is equal to 8 cm and MQ is equal to 2 cm. Find the radius of the circle. Solution. Join O and B. Let R centimeter be the radius of the circle. The center O lies on the line PQ. On applying Pythagoras theorem on the right-angled triangle OMB, we have thus the radius of the circle is 5 centimeters. Question 2 in the figure, AB and CD are two parallel chords of a circle with center O. AB is equal to 30 cm and CD is equal to 48 cm. And the perpendicular bisector from O to AB is 20 cm. Find the radius of the circle, the perpendicular distance between AB and CD. Solution. Join OB and OD. Draw the perpendicular ON from O to CD. Since AB is parallel to CD, MON is a straight line. As perpendicular from center O bisects the chord, AM is equal to BM is equal to 1 by 2 AB is equal to 15 centimeters. In right triangle OMB, we have thus the radius of the circle is 25 centimeters. In right triangle OND, we have thus the distance between chords AB and CD is 20 plus 7 centimeters, that is 27 centimeters. Question 3 in the figure, AB is equal to CD and OM is equal to 10 centimeters. Find the length of ON. Solution. Since AB is equal to CD, OM is equal to ON. Equal chords are at equal distance from the center. Thus, ON is equal to OM is equal to 10 centimeters. Solution. Here, OM bisects BC as well as AD. Therefore, BM is equal to MC is equal to 1 by 2 BC is equal to 15 centimeters and AM is equal to MD is equal to 1 by 2 AD. AB is equal to AM minus BM, that is equal to MD minus MC, that is equal to CD. Join OA and OB. Here, OA is equal to 29 centimeters and OB is equal to 25 centimeters. In right triangles OMB, so OM is equal to 20 centimeters. Further, in right triangles OMA, so AM is equal to 21 centimeters. AD is equal to 2 AM is equal to 2 into 21 centimeters is equal to 42 centimeters and CD is equal to MD minus MC is equal to 21 centimeters minus 15 centimeters, that is equal to 6 centimeters. Question 5 in the figure, AB and CD are two equal chords of the circle with center O. Name 3 pairs of congruent triangles. Solution. Here, OM bisects AB and ON bisects CD. Since AB is equal to CD, OM is equal to ON, AM is equal to BM and CN is equal to TN. Also, OA is equal to OB is equal to OC is equal to OD, all radii of the circle. So, 3 pairs of congruent triangles are triangle AOM, triangle BOM, triangle CON, triangle DON, triangle AOB, triangle COD. Relationship between chords and arcs. In the figure, AB and CD are two chords. Their corresponding arcs are APB and CQD.